Hello everyone. In this module, we can discuss the concept of differential phase shift keying. In the last module, we have completed the concept of phase shift keying as well as its transmitter and receiver sections. In this module, we can discuss the basic concept of differential phase shift keying. In the last module, we already discussed that this differential PSK is the non-coherent version of BPSK. Because we already discussed the coherent detection of BPSK and we have seen the complexity. So in order to overcome, even though its SNR is high, but the system of coherent detection of BPSK is complex. To overcome that complexity problem of BPSK, there is another method by using the non-coherent version. It is called as differential PSK. So in a simple terminology, we can say that differential PSK is the non-coherent detection of BPSK. And because this is a non-coherent detection, it doesn't make use of any kind of reference carrier or synchronous carrier at the receiver section. So coming to the DPSK transmitter section, here you can see that in the case of PSK, directly the original signal, that is the bipolar enarched, is directly multiplied with the carrier signal. But this is the for BPSK. But for differential PSK, it is a combination of differential encoder plus product modulator. Here you can see that in the differential modulator, the upcoming data bit is binary sequence, which is bipolar enarched, and that is compared with the past differential data bit that is represented as d suffix k minus 1. If you assume d suffix k as the current differential encoded bit, which is stored in the as a delay bit in the feedback section. So for the next upcoming binary data, the past differential encoded data is considered. So here this differential encoder, we can make use of either XOR gate or XNOR gate. This differential, we know the principle of XOR gate. So for if the two inputs are same, for the identical inputs, we know that the output is 0, and for different bit data, different input data, the output will be 1. So here if Bk is equal to Dk minus 1, then the Dk will be 0. If Bk is not equal to Dk minus 1, then Dk will be 1. And so here you are using XOR gate. So if you use XOR gate at the transmitter section with a delay element, this whole section is called as differential encoder section. This differential encoded data sequence dk is multiplied with the carrier to produce the DPSK signal in the form of dk into AC cos omega ct. Remember that this dk is also a bipolar enarched having two levels plus or minus 1. So the conclusion is that differential PSK is a combination of differential encoder plus PSK. So here this section is PSK and the first section is differential encoder. So differential encoder output followed by a product modulator produces the differential PSK. Here you can see that if you assume binary VK as the data sequence and past differential encoded data as dk minus 1, and then let us assume the differential encoder output as dk. If both the inputs are same 0 0, we know that the output is 0. For different inputs, and because it is bipolar, you can see that the voltage levels, if the data logic level is 0, the voltage will be minus 1, and if the logic level is 1, the voltage is plus 1. So for different data, you can assume 1 0, or for 0 and 1, you can see that the XOR output is 1 1, same, that is maximum magnitude. For same data, you can see the output as 0. So in the two cases, you can see that the output as 0 because here you are using the XOR gate. Here you can see that The differential encoder, we already discussed that it uses a XOR gate. It compares the decay, that is the current upcoming data sequence decay, with the, sorry, this is by BK with the past differential encoded data dk minus 1 to produce the current differential data dk. For example, if there is no transition between the present dk and past dk minus 1, then the differential encoded data is 0 with the developed phase as 0 radian. That's what here we mentioned. If there is no transition, then the differential encoded data bit is 0 with a phase change of 0 degrees. For example, if there is a transition from 0 to 1 or 1 to 0 in the second, as in the second case, that is, if both the data are different, then differential encoded data bit is 1 with a phase change of 5 radians. Let us see the operating principle of differential PSK. Here, the first two rows represents the transmitter section. First, here you are taking the binary sequence as 001, 001, 001, and 1. So it is a total of 10-bit sequence. And let us assume now you have to compare the current data bit 0 with the past differential encoded data bit. But because we are not aware of this past differential data bit, we are assuming the arbitrary data bit that can be either 0 or 1. Here in this example, we are taking it as 1. Now the past differential data bit is compared with the current data. So 0 and 1 are compared. If the data is different, we know that the output is 1. And again, the current data bit is compared with the past. This data bit acts as a past data bit for the upcoming data. And so 1 and 0 both are compared to produce the output data bit as 1. Now this differential data acts as the past data bit for the upcoming data. So again 1 and 1 are compared. So the resultant, we know that because of identical data the output is 0. So again 0 and 0 are compared because identical data output is 0. Again 0 and 0, you can see the output is 0. 0 and 1 different data, so output is 1. Again different data, the output is 1. Different data, the output is 1. Like that, the process is continued till all the 10 bits have completed. So finally, you will obtain the differential encoded sequence as 110, 001, 1101. Finally, we generated the differential data sequence. So in order to coming to the demodulation or detection, here first we'll take the phase change of decay. We know that when the data bit is 1, we know that the phase change is pi radians. So like that, wherever you have 1, we will take the phase change as pi, and wherever you have the data bit as 0, the differential data bit as 0, we will consider the phase change as 0. Like that, we will write the phase of decay. And similarly, we will write the 1-bit right-shifted differential encoded data. Here in this example, you can see that the encoded data is 1, 1, triple 1, 0, 0, 1, 0, 1. So take the 1-bit right-shifted differential data. So let us shift this data. So you will get 1, 1, 1, triple 1, 0, 0, 1, 1, 0, and 1 will be there. That is a leftover bit. Now let us write the phase of 1-bit right-shifted data dk minus 1. So here you have 1. So wherever you have 1, please take the phase difference as pi. And wherever you have 0, take the phase difference as 0. Like that, compare the phase of differential data as well as 1-bit right-shifted differential data to produce the output data bit. Here pi to pi, there is no phase change. So that's why the phase comparison output is negative. If you have negative, the detected data bit is 0. For example, here you can see 0 and pi. So you have phase change of 180 degrees. So you can take, there is a phase change that is represented by positive, and the corresponding detected data is 1. So like that, you can see that the demodulated output is same as the transmitted data. The transmitted data is 001, 001, 0011. So at last we have detected the demodulated the data which is proportional to the original message. So our conclusion is that when bk is equal to 1, so whenever the binary data bit is 1, then you can observe that dk is the complement of dk minus 1. This you can analyze here. Let us move to the previous slide. In this slide, you can observe that if the data bit is 1, in this example you can see, if the data bit is 1, that is B, Bk is 1, Dk minus 1, if it is 1, 0, you can see the outputs as 0 and 1. That is, whenever Bk is 1, Dk is the complement of Dk minus 1. For example, if Bk is 0, corresponding if you have dk minus 1 as 0 and 1, our dk is also 0 and 1. So whenever bk is 0, the dk is exactly equal to dk minus 1. And whenever bk is 1, dk is complement of dk minus 1. So you will have phase change only for the data bit 1. And for data bit 0, you don't have any phase change. That's what here in the next slide we have mentioned. Here you can see that when dk is 1, dk that is the current differential data is the complement of past differential data. When bk is 0, the differential data and the past differential data both are same. That's what here we mentioned. The basic difference between BPSK and DPSK is that in BPSK the phase of carrier changes for both the symbols 1 and 0. But in DPSK, the phase change is only for the symbol 1. This is when XOR gate is used. For example, instead of XOR gate, if you use XNOR gate, for symbol 0, you will have a phase change. That's what we have mentioned in the response. If BK, here I have taken BK as 001, 001, like that some sequence we have taken. So wherever you have the data bit as 0, you can observe that the dk is same as dk minus 1. And whenever the data is 1, you can see that dk is a complement of dk minus 1. So here dk minus 1 is 0, so complement will be 1. So like that, here phase transition is only for bk is equal to 1, not for bk is equal to 0. And now coming to the receiver principle, we already discussed that DPSK receiver principle is that it takes a comparator which compares the phase of differential data and phase of 1-bit right shifted differential data. The both are compared and that output is applied to the low pass filter and which is applied to the decision device. If the output of low pass filter is greater than threshold, the required data bit is 1. If the low pass filter output is less than or equal to threshold, the required data bit will be 0. So finally, the receiver DPSK receiver consists of a comparator which compares the phase of differential data and phase of 1-bit right shifted differential data, followed by low pass filter and decision device. For example, if there exists a phase difference between the magnitude of, for example, if you have phase difference, here it is phase is 0 and here phase is pi. There exists a phase difference between these two. Then the output data bit is considered as 1. Or you can see that the magnitude of low pass filter will increase. The magnitude of low pass filter will increase, then the required data bit will be 1. For example, if you have same phase like 0 and 0 or pi and pi, then the output of low pass filter will decrease. Once it decreases, automatically the output it is compared with the threshold, so required data bit will be 0. Coming to the bandwidth of differential PSK, in general, the MRA PSK bandwidth is expressed as 2FV by N. In differential PSK, we know that simultaneously you are comparing the current data bit BK and past data bit DK minus 1, past differential data DK minus 1. So simultaneously you are transmitting 2 bits. So that's why N will be 2 here. So if N is 2, the bandwidth of DPSK is FP. you can see that there is a reduction of bandwidth of DPSK when compared to BPSK. In BPSK, we observed that the bandwidth is 2 FP, but here the bandwidth is only FP. It is reduced to half. So coming to the advantages of DPSK, we already know that the principle is simple and the design is also simple, and it offers less bandwidth over BPSK. Bandwidth is FP, and for BPSK the bandwidth is 2 FP. And similarly, here the phase change is only for the data bit 1 if XOR is used. And in BPSK, phase change is for for both the data bits. These are the advantages of DPSK. So coming to the disadvantages, here we are not using the coherent carrier. Because we are not using the synchronous detection, sometimes there is a chance that there is an increase in the probability of error compared to the BPSK. And noise interference is also more. For example, if there is a bit error, then it will propagate to the entire sequence. So that is a drawback of DPSK. So in order to overcome the drawbacks of DPSK and BPSK, we can use a differential encoded PSK. So that is called as DEPSK, differentially encoded PSK. Coming to the applications, so the applications are like similar to the BPSK, that is in radio frequency ID tags or in Bluetooth communications or wireless LAN networking or commercial code division multiple accessing. We can use the differential PSK. I think in this module we have learned the performance of differential PSK transmitter and receiver sections. In the next module, we can discuss the differentially encoded PSK. Thank you for listening.